All right, while it's rebooting, let's get started maybe. I came early because I thought it'd be easier to install it. I'd rather do it here so you guys can see it. Okay, just in case you want to do it on your own, if you go to our class, you go to Files, Part 2, and you go to Supplementary Reading, you will see something here called Wireshark Intro. Okay, so this is like very introductory guide, and it will walk you, handhold you through step by step. I personally don't think you need to do that. You can, right? I mean, you can just use the tool. But if you need something, yeah. But just so we have it, let me download it. In case I want to show something from, actually there's some URLs I want from here. So that's why I'll download it. Okay, so let's try going to Wireshark. What? Wait, didn't I? No, that's not what I want. This is not good. Where is it? This is what I want. No, this is not what I want. Did we just install it? All right, someone want to help me? Where would I find the app after you install it? Frankly, I'm not a Windows user. Yeah, that's what I just did. I did exactly that, right? You guys saw me do it. But it finds my installer. Where's the actual app that I installed? Where's the link to it? This is my installer, right? Yeah. It's not what I want. I don't want this. I just installed it. Yeah? This one. Yes, thank you. Who caught that? Thank you so much. Yeah, I don't know why. Okay, thank you. So I don't know why it wasn't finding it when I searched for it. All right, let's go here. Okay, so here, so on this one I have Ethernet. I'll show you on my Mac as well. I'm using the wireless, okay? But here, so what we're going to do in Wireshark, so remember Wireshark is a packet capturer and a packet analyzer, meaning it ships with a packet capturer, and it has it recognizes protocols and it dissects them and it kind of shows you what's inside the packet. But what you have to do, and it sits at layer 2, right? But what you have to do is you have to choose a network interface. Right? When we say layer 2 is layer 2 of an interface. So here so this computer to wired Ethernet. So that's what I have. So I'm going to choose that adapter here. Okay. Now we can do a couple of things. So let me just click on that. So you can see it's going to start to capture all the packets flying around on that wired Ethernet interface. Okay? So that's what we're seeing here. Okay, but for example, if I want to, so I can do two things. Right now it's capturing every packet, and I can choose to display certain packets. So for example, I'll also show you how I learn about things. So let's say I want to learn, so there's a display filter. So you just type that, and it will show you how to do the display filter, right? So let's say we want to look at port 80, okay? So TCP port, so let's say so we're going to use TCP port 80, which is what web servers run on. And here I can put a display filter. So 25, anyone know what port 25 is? Does anybody know? So when we talk about TCP, we'll see that there's a concept of port number. And a port addresses a process. And many of the lower ports are reserved by the system. So 25 is a small port number. Does anyone know what it is used for? What process? It's SMTP, which is mail. Okay, so mail runs on port 25. Web servers, mostly by default, run on port 80. Okay, so we're going to change this to 80. Okay, and now what this is going to show me is all of the kind of the web traffic. All right? If we go back to 25, you should see there should be nothing because I'm not running a mail client right now. But let's see, I'm curious. What happens if I did do 25? Yeah, there's nothing, right? Because I'm not running. If I put up Outlook, actually Outlook, so SMTP is like a simple mail transfer protocol. These days, we use slightly more secure, right? If you go look at Outlook, there's another port like 557 or so I can't remember right now, but it runs on a different port that's a bit more secure. Okay, but let's go to port 80. Okay, and we can see this is the web traffic. So you can see, for example, let me see. For example, this is a get from. So what we can you guys see? Is this clear? Is it big enough? Is not big enough. I don't know how to make this bigger. Can I make it? Yeah, I can. Okay. Is that better? Okay. So we're looking at this get here. Okay. There's a at this packet. There's a time here. This reference is something like. There's some internet time protocol. So right now we can't really make sense of it, but it's at this time point. But what we see is there's a source and there's a destination. So let's, if we go to terminal, okay, in Windows it's command tool, right? Okay, we go to a command prompt. I don't know how to make this one bigger. Does anyone know how to make this bigger? Thank you. See, you have people who know Windows. I don't know. Okay, good. So, so I'm doing ipconfig/all. This shows me all of the network interfaces, and this is my Ethernet here. And if you look at my IP address, my IPv4 is 10.245.93.1. Come here, you see this packet is get, or there's a request here from 10.245.93.1. So that's a request from my computer, from this computer, to this. No. Did I get that right? Let me see. 10.245.93.1. So what you'll see when we talk about network layer and we talk about IP, there are reserved ranges of IP addresses that are reserved for private networks. So 10 dot is a range of reserved addresses. Does anyone know any other? For example, what's your IP address? Can you check your IP address? You know how to find it out? Are you on a Mac or a Windows? Yeah, just do ipconfig/all and look for IPv4 address. Oh, you're also 10 dot. Okay, is everyone 10 dot here? Is anyone 172 dot? No. Okay, they must have configured. Usually the wireless network on campus is 172 dot. And that's another reserved addresses, a range of addresses. Does anyone know any other, like maybe from home? When you set up your home network, what do your IP addresses at home look like? 192.168. Not 192, but it's 192.168. That's a set of reserved addresses. So there are these three sets of addresses that no one on the public internet is supposed to use. therefore private network. So that's what we see, 10.245. So remember, I'm on this one right here. Okay? This 10.24593.1 was me. Okay? And I'm sending a packet to 172.25.5.12. And if you look at what that packet is, so it's a HTTP packet. This is a hypertext transfer protocol. This is a protocol that sits at the application layer, and it's what you use to transfer data, right, to surf the web. And if you look at it, we see, what Wireshark will do is it will go and dissect this packet for you. It will show you what, this is the, so at the link layer, there are framing bits, right, that are at the beginning, at the end, that basically delineate that packet, that frame. And so here are the framing bits. Okay? Again, I'm not going to focus on this too much, but wherever you studied about the link layer, you'll find it here. But what's going to be important is that in addition to the framing bits at the link layer, you have the Ethernet protocol. And Ethernet protocol uses MAC addresses. And so if you open that up, you'll see that it will show you the source MAC address, okay, which is this right here, and the destination MAC address. So let's go double check that. So if I go here, and you look at, again, my Ethernet adapter, this is just using ipconfig/all, and you look at this address here. Okay, this address is the IP address of my Ethernet network interface. Right, remember, the MAC address is something that's tied to a specific network interface. Right? If you come here, so 047C16, 047C16, and then I think you can check the rest, right? 2A8AB1, 2A8AB1, right? So this is good. The link layer, the Ethernet, at the link layer, the source and MAC addresses match. Now, this is the MAC address of the destination. But which destination do you think this is? So let's say I send a packet from here to Google. Do you think this is the MAC address of Google's web server? So think about that, okay? I want you to think about that. But if we go to the internet, the sort of layer 3, and we look at the header of layer 3, again, we also see a source and destination. This is the IP address. This is the layer 3 network address. What was that? Ethernet was the layer 2 address. It's the MAC address. So you remember my IP address was this, okay? And that matches what's here, right? But the destination is 172.25.5.12. So this is the final destination. So I'm sending a packet from my computer to whatever 172.25.5.12. So my question for you is this MAC address, the destination MAC, the MAC address of this machine? So the IP address identifies a network adapter. So does the MAC address. It's supposed to be tied to a network adapter. So do you think that the 00000C9F49A is a MAC address of 172.255.12? They both say destination, right? What do you think? Who says it is? Who says it's not? What do you think it is? Yeah. No, I don't understand. There's machine and router. Here, right now, we should be talking about network interface. Yeah, are those two the same network interface? And if not, why not? Okay, how about you? IP address does not refer to a set. IP address refers to one network interface. But I like the way you're thinking, but IP address refers to one network interface. It's the address of an interface. So anyone? Somebody here also said no. Did you say no? Yeah, so what do you think? Are these the same? Okay, so what is 172.25.5.12 is what? Is the IP address of what? Of what? Right, of the final. If I'm going to Google, it's Google. What is the 00000C? What is that the MAC address of which network interface? Sorry? Which router? So somebody said Cisco because somebody was smart and read some information there. Which one? Huh? Okay, NUS, correct. Router is all correct. Can you generalize it? Yeah, who said that? Yes, it's the next hop. Correct. Okay? So this is the next hop. So this tells you this very important point. Link layer scope is not broad. The link layer scope is only hop by hop. Network layer scope is broad. It's the entire internet. It's what you said. But this is the network address, the IP address of the final destination. Okay, this is going to come into play. I want you to remember this. In a packet, the packet sent from me out to Google, there's a route, right? The next hop is captured in the link layer. The final destination is captured in the network layer. Okay, so that's good. So we can now, so today we're going to start talking about this transport layer. Okay, so this is the layer 4 header. And in the layer 4 header, you're going to see something called port number. That's the destination port. So I'm talking to Google, let's say, and Google's web server is running on port 80, because as I said, by default, web servers run on port 80. HTTP traffic by default is port 80. You can change it. That's why I keep saying by default, because you can run a web server. It's basically it's a client socket type of thing, and you can have it listed on any port you want. Okay, so if you want to run your own port and run it on port 8080, you can, or 8000. But what you cannot do is run it on port 25, because that's reserved for SMTP. You can't run it on a reserved port, but you can pick any large port. Port numbers are 16 bits, so any very, very large port. Okay, so look at the source port. The source port is 55509. So what do you think that is the... So again, we haven't learned this, but this is kind of getting your hands dirty quickly. Port numbers address processes. So what process do you think 55509 is a process of, is the ID of which process? Can anybody tell me? Yeah.
It's not the ID of the process, first of all. It's like a process.
Uh-huh. Yeah, so no, it essentially is the address of that port now. Address of that process, effectively. Yeah.
But
yeah.
Maybe a web browser or something like that.
Yeah, exactly. So this is the port, this is the process that generated this packet. For example, it could be my web browser. Like right now, I picked an arbitrary one. So I'm running. I think I'm only running this, right? And there's only there's a few tabs, so it's one of these tabs. Now, I'm not very good at this. On Windows, is there a way to get information about processes? Is it like I could do it on my Mac, but what is it on Windows? Anybody know? Is there a way to get a list of all the processes? Thank you. So let's run that. Task Manager or Task Monitor? Is Manager the same thing? Is it? Excellent. Thank you. See, I'm using this as a way to learn from you guys too. Because I stopped using Windows a long time ago. And then this is what, Windows 10 or 11? 11, right? So I know nothing about 10 and 11. The last I remember was probably XP. Long time ago, right? Okay, so let's, I can't find port number though. Details? Yeah, there we go. Yeah, this is exactly like on Mac and Linux, you can run top. This is exactly like top. Good. Okay, so can we search by any chance? No. So what do we say? It's 55509. Maybe can I sort? Yes, I can sort. Oh, it's not showing me everything. Why? I don't know. Okay, I mean, I won't find it right now. Somehow this only goes up. But you get an idea of what the port numbers are, right? This is the process ID. Okay? Oh, sorry, no. I'm wrong. It's not process ID. That's not what I want. I'm wrong. How can I see the port number? No, I need to see the port number that the process is running on, that is listening on. Sorry, the process ID was wrong. This is just a process ID. If I want to kill the process or something, yeah, it's okay. We'll figure this out. But anyway, I think, what's your name? Max, right? What Max said, it's the process that generates. Like it could be, for example, in my case, it's probably this edge. Okay, and what you find is that every tab is going to be its own process, right? Why do you need every tab to be a process? Tell me, why can't Edge have a process ID? Why does every tab need a process? Yeah? Do you know? But tell me, why does every... So I claim every process needs an address or identifier. So Edge here seems to be a process, right? But I'm claiming maybe every tab needs its own process port. Why? Hang on, Max. Why? Do you know? No. Okay. So can you work with me? What's your name? Don't worry. You can laugh. I'll laugh with you. What's your name? Winnie. Yeah. Winnie. You surf the web, right? Yeah. Don't say no, because I'll be very surprised. And I'm sure you have. Are you one of those people who has 100 tabs open? No. Oh, I am. But you have more than one, right? Yeah. Or not? One, right? So on one you might be watching YouTube, Facebook. No one uses Facebook here, right? I just dated myself. Instagram, TikTok, none of those. But email. So email, YouTube. A bunch of things, right? So let's say a packet. So let's say this is your computer, okay? And on this computer you have Chrome or Edge or whatever, Firefox running, multiple tabs, okay? One is email, one is YouTube. So now there's a Ethernet or wireless interface here, and a packet comes in, right? It's an email packet. Where do you want it sent? Yeah. And is your email... It's a tab in Chrome, right? Right? And where do you want your YouTube packet to go? Yeah, so you can't just say, send it to Chrome. So Chrome, as a process, cannot work, right? Chrome itself actually can generate many, many processes. In fact, what you'll find is that every web request might actually generate a new process. Yeah, Max, you wanted to say something?
No, that's it.
That's it, right? Yeah, okay, good. Yeah. Okay, Winnie, are you with me? See, so if you don't know, it's okay. I'll help you logic things out. All right? So we see that we come here. So again, so we see some port numbers here, and you see a whole bunch of other things. So let's see if you guys were paying attention last time. What's the main job of transport layer? Yeah. Right. Do you see things here that support end-to-end reliability? For example, sequence number, right? Why do we need a sequence number? Because I want to know if I missed anything, right? Sequence number, if things are sequencing up and it goes from 5 to 8, you know you missed something, okay? So we'll see that that's there. We see something like acknowledgement. Why acknowledgement? Because, well, if the sender is sending 1, 2, 3, 4, 5, and the receiver only got 1, 2, 3, didn't get 4, there's going to be this acknowledgement mechanism. There's no way for the sender to read the receiver's mind. We use an acknowledgement scheme. So you see acknowledgements here. You also see window size. Window size, I think somebody last time, who was it last time who talked about congestion control? Somebody mentioned congestion control last time. Are you here? Are you brave enough to raise your hand? But congestion control is about how much data you pump into the network, right? When there's a lot of congestion, you're going to push less data. When the network is good, you're going to push more data. That's determined by window size. Okay, so that's part of reliability. And then finally, we see a checksum, right? Here, so checksum, this is the same checksum that you studied at link layer. Remember there was a CRC, right? The cyclic redundancy check. But I want you to just think of CRC as just error detection. Try to generalize. CRC is nothing magical about it. It's just the error detecting code. It's a way to add redundancy so you can detect if an error happened. And it turns out that link layer, network layer, and transport layer all have a checksum. And does application layer have a checksum? So I'm telling you, link, network, and transport layer have a checksum. And so my third why question, by the way, is why are there so many damn checksums? Right? That's my third why question, but we won't talk about it right now. But I'm asking you, does application layer have a checksum? Max?
I think it depends on the protocol you're running, but I'm actually not sure if XMPP again is a checksum.
Yeah.
But it might be because it's very easy to calculate it.
Yeah.
Very easy way to
Yeah, Max, you're absolutely right. It depends on if the application implements the checksum. It's not part of the TCP/IP stack. What is part of the TCP/IP stack is link, network, and transport layer checksums. Right? And I didn't show you before, but we see the checksum here. We should be able to see the checksum here. Right? So there it is here. Okay? And then we should be able to see the checksum here. Well, where is it? I don't know. Maybe it's here. This is interesting. This is framing. All right, we'll have to debug this. Maybe some enterprising student can figure out where's the checksum for the link layer. Okay? And then, so that was up to transport layer. And then finally, we get to the, yeah, Max?
Could it be that the checksum for the link layer is not displayed as the hardware screen?
Yeah, exactly. That's what I was thinking. Good. I think you read my mind. Yeah, exactly. Okay? So we got through link layer, network layer, transport layer, and finally, we see that this is the application layer. And in the application layer, there's a whole bunch of information here. Let me see. We can actually look at, we can't see here, we can see the get. Yeah, again, we didn't figure out what this packet is anyway, but let's try this. I'm going to go to a link. So in the Wireshark intro, there's a link that is very easy and very easy for us to check. So here it is, yeah. Okay, so now what I'm going to do is, I'm going to go here, I'm going to paste the link. Okay, I'm not going to hit enter yet. Let's clear this. And let's actually stop this. And I'm going to show you something else that we can do. Okay, now before we start capturing, we can actually, so what we did before was we captured everything, and then we did a display. We filtered. Everything's there, we only are looking at certain packets, but we can actually restrict these things to only capture certain packets, and that's called a capture filter. And we can, again, this was a display filter. Let's look at how to do a capture filter. Brother, I'm doing this so that I want you to see how I function. I don't memorize stuff. Right? So you don't have to memorize stuff and have people handhold you. You can figure stuff out. As long as you understand what is possible, you can go find the syntax. So here's a capture filter. And the way you do it is, let's figure this out. Where is it? Why is this not telling me how to do it? This is a bad link. I don't know. This is because I'm on Bing. That's why. Sorry. Usually I search usually serves me well. Yeah, there you go. That's what I want. So here we go. So here, we can just write, for example, if I want to just capture, there, just port. So let's just capture port 80, okay? So come here, I'll type here, port 80, okay? On Ethernet, and we'll go. Oh, there's a lot of stuff. I didn't realize that, okay. But anyway, we're going to do my... I'm here, right? This is... Okay. See if we can figure this out now. It's too much here. I'm getting very confused. Okay, I think it should be this one. No, this is not it. Okay, this is horrible here. Let's go figure this out. How to do this. Can I? Oh, I can do IP. Okay, IP dot destination. Let's figure this out. So again, we'll come here. Let's see if we can. Okay, Windows. Okay, what was the address? The address was. Oh, that's not what I want. Oops. The address was gaia.cs.umass.edu. Okay, so. Okay, so we want the address to be this. Okay, and the syntax was, if I go back here, the display filter, ip.dest equals this. Okay, so let's do that. ip.dest. Okay, there we go. All right, so this is packets that I'm sending to that remote web server at University of Massachusetts, right? This is coming from that Wireshark intro. Okay, and you notice what we did, just to show you what we did was we went and got this file. It says, congratulations, you've downloaded the first Wireshark lab file, right? So okay, so here is the packet from me. Remember, I'm 10.245.93.1, right? And again, if you go look here at the Ethernet, you will see, again, the same next hop. Even though the destination now is 128.119.245, in the US, the MAC address destination is the same, because it's the next hop. It's not surprising that since I'm connected to a router, the next hop is the router I'm connected to. Okay? So we come here, we look at HTTP. This is the GET file. So this is just a request. If you look a bit further down, you will see, again, this is another GET request. I had one here, another GET request. We'll talk about why there were two in a minute. But eventually, there's going to be a response, right? Oh, because I only did destination equals this, right? Oh, I can't say or, right? Can I do an or? I want the, okay, so I can also just change this to source. So this is now the response from the remote web server to me. Okay, and if we look at that response, you will see that it sent exactly what we saw. Right? So, like, all this is clear text. If most sites right now run HTTPS, right? Which means that the data is encrypted, so you wouldn't be able to see it. But there's still some unencrypted, at least for learning. So we can see that exactly where what you see on the web browser, where it is in the data, in the packets. Okay? Okay, so there was an interesting thing, right? Why? So when we had this as the destination, right? You saw, so you saw there are these SYN packet, right? So it turns out that TCP is a connection-oriented protocol. That when it wants to set up a connection, like when you want to talk to a web server or something, there's a setup. This is for oriented protocol. So what happens is A wants to get data from B. You are A, let's say YouTube or whatever, Google is B. You're going to send a packet, the SYN packet, a SYN packet. Google or B is going to respond with a SYN ACK, and you're going to respond with an ACK. That three-way handshake, I can't show it here because I'm here filtering by destination. So these are the two packets to the destination. The SYN ACK will be shown if I make this the source. Then you see the SYN ACK here, right? So that's the SYN ACK back to A. And A is going to send an ACK back. That's the ACK. And then only after that three-way handshake do I send my request. Okay? So every transfer starts off with this. Okay? Okay, so I think maybe as a first cut, introduction to Wireshark, this is all I want to say. Are there any questions? So I encourage you to play around with this. Go look at the different packets at the different fields and tie them to what we learned in class. Okay? Now, you can see why this is a good tool for debugging, right? Because it tells you basically everything that's in the packet, and if something is going wrong, if something is being set wrong, right? For example, if you were trying to do MAC address filtering, like a lot of DHCP servers, what they will do is they will do MAC address filtering. You can say, I only want network interfaces with these specific MAC addresses to be able to connect to me, right? In fact, that's what NUS does in my lab. If I have a port, if I have a network interface and I want to connect something to it, and I want it to, for example, have a static IP address, I've got to inform Computer Center of the MAC address of that network interface, and then they will configure it. So that's essentially MAC address filtering is used a lot for access control and authentication, right? So if something is going wrong with that, you can debug it by looking at the packets and so on. By the way, I think you must have learned this, and maybe I said it, but the MAC address is something that's burned into the network card, quote unquote, burned in by the manufacturer. So it's set by the manufacturer. But actually, it's just a field in a packet, right? Which means you can change it. So you can spoof MAC addresses. It's not very hard, right? You just have to go and intercept the packet and change the MAC address. I'm not suggesting you do that. That's going to mess up your networking, but it's burned in, but it's it's meant to identify the manufacturer actually. Okay, good. So if there are no questions, let's move on. I want to ask you one of my first why questions. Okay. Let's use WordPad. Ooh. So you see, I learned who was the one who taught me about the press Control and scroll. I learned. but it's not making the font bigger. It just made the... Let's try doing that. Okay. Okay, so let's ask this question. I can make it full screen. Okay. The question is, why do we have, or maybe the have is the wrong word. Why do we use both MAC and IP addresses on the internet? I don't like this. It's using too much space. Can I turn it into a bullet? This is irritating. Okay. It's fine. Can you see that? Is that big enough? Is it big enough? Yeah? Okay. So why do we use both MAC and IP addresses on the internet? So anyone want to be brave? Okay, if you've talked to me about this, some of you have, just kind of keep it quiet for a little while. Okay? So why do we have, does anybody know? Does anyone want to venture a guess? So the fact is we use both. Okay? Yeah. So the internet is very big, and the MAC address is used to determine the network. Yeah, and the MAC is used to somehow address the host. Yeah, you're on the way. Yeah, I like the way you're thinking. Anyone else? Yeah. IP address is shared, yep, and MAC addresses are not. Okay, good. But does that, I mean, so that's a fact about IP and MAC. Does that explain why we use both? Okay, so somebody should challenge me and say, why is this a question worth asking? Yeah? Yeah, exactly. Yeah. Yeah, exactly. Yeah, so you're correct in terms of your statements. So I like the way you're thinking, Max. So all of you are good. So let's take a step back and address what Max just answered, which is why is it a question worth asking, right? Is why do we have two addresses? Right? So for example, tell me your name. Spell it for me. Benita. Okay, why? Okay, I think I asked last time, but I'm sure you have a place to live. And I'm sure you have an address, right? So let me ask you, how many addresses do you have? One. So if I want to send you a letter, I need one address, the one address you have. Okay, so does that make sense? Is the validity of the question clear? Right? I mean, we typically need just one address. For example, the postal system. Right? So that's why this question is an interesting question. This is why it bugged me for a long time. When I started learning about networking, this bugged me. Why do we have two addresses? Or not have, why do we use two addresses? You can have many addresses. You just don't use them, right? But why do we use them? So that's the question. Why do we have two addresses on the internet instead of just one when in the postal system you just need one? And so this is a true fact, okay? This is a true fact. On a connected network, you need just one, and I'm going to leave this blank, and somebody's going to help me. Fill in the blank. You need just one, what? What kind of address? Huh? No, this is an English word. Yeah, louder. Say it. Who said it? Unique, exactly. You need one unique address. Because, Benita, if you and I have the same address, can the postman know where to send the packet to you or to me? Yeah, if we have the same address. If you live in Sentosa Cove and I'm living in Clementi, I know this profs live in Clementi, right? But we have the same exact address. Would the postman know? Right? No. So a true fact. On a connected network, you just need one unique address. Okay? And the internet is a connected network. Right? So, okay? So, yeah, so then the question maybe, so you'll notice that I'm going to ask a lot of questions, but I hope in that process you learn to ask questions as well. Right? When you want to answer some, yeah, you want to say something?
I think it's because like usually the router is to establish the connection. So like the MAC address is the internet, or usually the IP address for that. So it's like it needs that additional address first to establish the connection.
Okay, I don't deny there could be a system where you do that. But I wouldn't agree that you need that. For example, I could just, you guys probably know this, or if you don't know, I'm telling you, you can manually assign IP addresses to all your computers. So yeah, the sysadmin can come in and give all the IP addresses to everyone. Yeah, so I don't need a MAC address to get an IP address. Okay, we'll get back to that. It turns out MAC addresses are unique, but that's okay. So true fact. On a connected network, you need one address. Anyone want to disagree with that? That if you have a connected network, like our postal system, right? Every house, the roads connect, right? You can think of the roads as being the links. It's like just like the internet, where you have network interfaces. So on a connected network, and by connected network, we mean that there exists a path from any node to any other node, right? If A and B are quote-unquote connected, it means there exists a path from A to B. And A can initiate the connection or B can initiate the connection, but either one can find the connection. That's what connected means. So in a connected network, you need one unique address. Max, you had your hand raised. Yeah, yeah. But okay, so maybe we can modify this statement to say at any given time on a connected network, you need one unique address. So you're correct, but you can change. What I think Max is saying, and many of you are thinking, is IP addresses can change. MAC addresses are not supposed to change. So assuming you don't spoof, MAC addresses are fixed. Maybe that's what's going on. It turns out no. Because on a connected network, you need one unique address. Yeah. So I'm a big fan of like logic. And so we always have to start with things that we know are true. And then we can use logic to get what else is true. So that's why I'm emphasizing it. Okay? So this should tell you, now, if you disagree with the true fact, speak now. Because you have to agree or disagree with that fact. I can erase the word true and say claim. Okay? If somebody thinks it's false. Do you all agree or not? Max, do you agree that you just need one addressing mechanism? Because if you don't, I'm going to ask you, why does the postal system work with one address? And you have to be able to answer that. So I almost think that you can't argue with this. But if somebody wants to, go ahead. I will convince you otherwise. Yeah. But the city is part of the address. Isn't it? No, I'm just in the postal system, your city, like you go to the US, 10 random road, comma, San Francisco, comma, California, right? Comma, something, right? That's the address. Yeah, so you're right. The city is part of the address. In fact, you could argue the country is part of the address and take the whole world. You could have like you guys, there's a recent article that I saw, there's a Singapore somewhere in Texas. Oh, no, in South Africa, right? Somebody was saying there's a Singapore in South Africa. Did you guys read that? Yeah, so, but it's Singapore, comma, South Africa, right? So yeah. So I like the way you're thinking, but there's a unique address. And you have one address. Yeah. Yeah, okay, so, but do you agree with this fact, or do you think this fact is wrong? On a connected network, you need one unique address. Yeah, I mean, you're trying to answer the top. We'll get to it in a second, but I'm curious about your opinion. Is it true that on a connected network, you need one address? What do you think? Yes or no? Yeah. Okay. How about you two? Yes or no? Do you agree or not? Okay, so what this should tell you is that, again, if you accept this, so you need only one addressing mechanism. IP or MAC. Right? Now IP addresses by definition are unique. Now they can change, but you're not supposed to, the protocol does not support you assigning the same IP address to two network interfaces. You can do it, as I said, you can manually do it, but then you're violating the protocol. And MAC addresses are decided by the manufacturer, right? In fact, there's a body. I think it's like ICANN, or there's a world body that assigns to manufacturers blocks of MAC addresses. Okay, and then they are supposed to assign them to each of their devices that they make, and then those devices get shipped around the world. Okay, so TSMC, Global Foundries, if they make network interfaces, they have blocks of MAC addresses. So MAC addresses are actually supposed to be unique, and IP addresses are supposed to be unique. So both can work, right? So you can, now this is going to blow your mind, you can build the internet with only IP or only MAC addresses. Yes, you can. Do you believe me? So, but you have to believe me. Why? You agreed with this fact. If you don't believe me, then you disagree with that fact, right? Okay, so this is in fact true. So the only question you have to handle, and Max, this is going to get back to what you said before, okay? Which one is preferable? So the question is, would you build the internet with IP addresses, or would you build it with MAC addresses? Now, let's take IPv4. On one hand, IPv4 is 32-bit address, right? Which means there are 4 billion IP addresses. 2 to the 32 is about 4 billion. MAC addresses are what? 48 bits, right? So there's 2 to the 48, which is a lot more. So that sounds like an argument to be made for using MAC addresses to build the internet. Anyone want to give an alternate reasoning or choice? Yeah. Why? It's very inefficient lookup. That's what Bonita said. Why? Yeah, exactly. So what Bonita is talking about is about searching. Like when you want to do routing and so on, you just search through your routing tables. Yeah, you want to say something?
I was going to say that with the postal service, your
Yeah.
a lot of the internet, it's so variable that I can change this much.
But that's easily fixable, right?
What?
That's easily fixable. If your house changes, you just need to have a central repository that you inform, right? I mean, people move, don't they? People don't live in the same apartment their whole life.
Yeah.
So when you move, what do? You inform the post office. Yeah, so maybe you say, oh, but you do that only every few years. But that's like a detail. I could move every day if I wanted. Not very smart, but I could. Yeah, so I like the way you're thinking, but the fact that you shift houses is not a reason. The fact is you can't take your address with you when you shift house, though, because the address of the house remains fixed. If you move to a new house, you have to have a new address. That's the uniqueness. In a connected network, you need a unique address. So I like the way you're thinking, but I think you're thinking maybe it's like inconvenient. But that doesn't stop us from doing it. Yeah. Anyone? So Benita says something about search, and Max, you said something earlier, yeah. Yeah. So what Benita, you said about grouping things together, we say IP addresses are hierarchical. They have a structure. Okay, so IP addresses that are similar, right, or interfaces that are geographically close together have similar IP addresses, right? For example, a lot of Singapore is 137 dot, right? It turns out I saw some other IP addresses in Singapore now, but 137 dot is, you can be sure that that's a Singapore address, right? That's why if you go to like, what is my IP address? Actually, that website will tell you that you're from Singapore, will tell you, or you're connected to Singtel or M1 or whoever your ISP is, okay? So IP addresses are hierarchical, but MAC addresses are not. Wait, but I thought I just told you that every manufacturer is given a block of IP addresses. So why they're not hierarchical? Yeah, hang on, Max. Yeah, Benita, why are they not hierarchical? Yeah, because Texas Instruments has a block, Global Foundries has a block, TSMC has a block, Chartered has a block. Sorry? Yeah, that's right. Yeah, Max?
Yeah, it's like Apple has a lot of
Yeah.
MAC addresses. It's not saying that you cannot route based on information because MAC number
Yeah.
will be US and MAC number.
Yeah, exactly. Yeah, it's like what Benita said. They sell them and they get shipped throughout the world. So in some sense, MAC addresses are flat. They're unique though, but they're flat. Okay? So if you had a choice, you would choose. Now, people didn't ask me, why does so if you have MAC addresses are flat, which means your routing tables would have to contain all possible 2 to the 48 MAC addresses. But people didn't ask me, why does a hierarchical structure make routing tables more, scale better? Do you know? Yeah. So for example, I told you Singapore is 137 dot, right? Which means the rest of the world, and let's say there's 10 million interfaces in Singapore with 137 dot. But the rest of the world only needs to store in their routing table 137 dot. That's it. That one prefix captures every computer network interface in Singapore that's 137 dot, right? Yeah, that's why. So the routing tables outside Singapore just need to store 137 dot. When they see that, they need to route that packet towards Singapore. That's why the routing tables become more scalable when you have hierarchical IP addresses. Hierarchical addressing mechanism. So which one is preferable? So let's get some facts. This is Okay? This is why. So which one is preferable? You need to realize that IP addresses hierarchical and MAC addresses are flat. So IP addresses are preferable, meaning if you only have to choose one, okay? So I hope in asking these questions, we've already learned a lot, right? Like, have you learned a lot? The point is, the final answer, it turns out, not going to matter so much, right? But the questions we ask as we are proceeding, those questions, those probing questions are meant to help you learn. Okay? So we see that I could build a network, internet, with just IP addresses, and everything would work fine. I could build a network with just MAC addresses, and everything would work fine to a certain extent, except, as Benita said, my routing tables would become huge, right? 2 to the 48. I don't even know what that is. That's like 42. It's 2 to the 16 times 4 billion, right? Okay? So now it feels like we've gotten nowhere because we still haven't answered the question, why do we have 2? Okay, so for that, we've got to look at how, okay, so at this point, let's take a look at what. So I think if I ask you guys what, meaning how are IP and MAC addresses used, you guys can tell me, right? How are they used? Not why do we have 2? That's a deeper question. How are they used? I think most of you will say, I think, Benita, you said IP addresses are used to identify the network, and then MAC address is used to somehow identify the host, the network interface, right? So that's a true statement, right? Typically, when routers are forwarding, they look at the IP address and they decide what the next hop is, because remember, it's a the network layer's job to do routing. The network layer decides the path and the next hop. So it uses IP address to do that. Now, once I get to, let's say, like the second to last hop, we know that in the second to last hop, the next hop is the destination, and they're going to be in the same local area network. Right? Typically, that second to last hop will be the gateway or the router for that LAN. So now let's look at what happens in that LAN. Okay, or let's call it Ethernet. So suppose it's an Ethernet. Suppose that, like, people in let's say the first 3 rows, we're all in a LAN. Okay, there's 5 of us. Okay, 4 of you and me, 5. Okay. Now let's say that. So what did you learn about Ethernet? Like, give me a fact about Ethernet. Like, something should come to your mind. I mean, there's a reason why there's protocols like CSMA, right? And so on. Yeah. Ethernet is a broadcast medium, right? Meaning that on that wire, when one node transmits, every node can hear, right? In that same way, wireless is a broadcast medium, right? So that's why in wireless you also have, CSMA is from Wi-Fi, right? What's the one on Ethernet? Yeah, it's like, yeah, exactly, yeah, okay. So, but you have a mechanism because both those are broadcast mediums, right? So now let's go back, let's assume Ethernet. Let's assume the 5 of us are connected on an Ethernet. If I'm downloading, now let's assume, for the moment, uniform traffic. So the 5 of us are downloading a file, so the traffic coming in is uniform, right? What does that mean? That means how much of the packets are meant for me? Of all the packets coming in, what fraction is meant for me? What? Yeah, 1/5, 20%. How many are meant for you? Yeah, how many, what fraction of the packets are meant for you? I'm talking to you. Yeah. Hang on. Hi, I'm talking to you. You, yeah. Yeah, you're in my network, right? But are you with me? We're on a network. Okay, 5 of us. 1, 2, 3, 4, 5. 5 people. Assuming there's uniform traffic. We are all downloading stuff from YouTube, but uniformly. So what fraction of the packets are meant for you? But there's 5 of us. So 1/5, right? 20% of the packets for you. How many packets are for you? How about you? 20%, right? So, but we're in a broadcast medium, so you see all 100% of the packets. What do you have to do? Yeah, how many are not meant for you? Yeah, 80%. So you have to reject 80% of the packets. Where is that rejection done? How? Where is it done? Yes, you're correct. It's done by the network protocol. Max? Well, let's say I'm building a network with IP addresses. No. So if I'm using IP addresses as my addressing mechanism, then I'd have to, and an IP address right now is only exposed at layer 3, right? The network layer. So the network layer would have to reject the packet. That's what I'm getting at. Saying the network interface is correct, but not meaningful. Where is it rejected? It's rejected by the network layer, right? Then if so let's write that down. So we can say Ethernet is broadcast. Yeah, my typoing is horrible, right? Ethernet is a broadcast medium, so every node hears So this is where we were. This rejection is done by which layer? So if you build a network with IP addresses, it needs to be done by layer 3. If you build a network with MAC addresses, it's done by layer 2. But we saw that it's not so preferable to build a network with MAC addresses, because MAC addresses are not hierarchical. Okay? So does that help you? Now, what's the advantage? So we saw IP addresses have an advantage in terms of routing. But we see that at the very last hop, if I reject packets at layer 3, what does it mean? It means I've done a lot of processing at layer 2 already. I'm processing 100% of the packets through layer 1 and 2. I'm doing a lot of extra work at layer 2. So perhaps I have another addressing mechanism that's exposed at layer 2 that allows me to reject packets. Right? And that's the anticlimactic reason why we use both. Okay? Because it's a little bit more efficient, right, to reject the packet at layer 2 than it is layer 3. Does that make sense? But you should get it all out of your head that you need to do that. You don't. Okay? Keep that in mind. You don't need both of them. One is enough. And I hope the sequence of questions here, again, just helped you learn. So the answer would be with Okay? And this is why we use the MAC address. Any questions? Again, a bit anticlimactic because there's no big revelation, but I hope the sequence of questions here were useful. Okay, so this is kind of everything, right? Yeah. Yeah, this is everything. Okay? Good? Any questions? Let's take a break. We take a short break, come back, and start transport layer. Okay, I know this went a little bit longer than I wanted, but it's okay. I think it was worth it, right? Okay, we'll come back at 11:30, and then we'll go for another 15 minutes, but I want to start transport layer today. All right, thanks. Yeah? Exactly, right? Because layer 2 involves a lot of work. There's framing stuff to do, there's CRCs to compute, there's things to do. And there's no point you want to do them for, like in this case, 80% extra, it's not 80% extra work, it's like 400%, no, almost, yeah, 400% more work. Yeah. Yeah, it's a performance thing. It's an engineering reason. There's no fundamental reason. Yeah. Why can't the MAC be a subset of IP? Well, traditionally, if you remember, the MAC is assigned by the manufacturer. The IP address is not. The MAC address is not unique anymore. Right? If it's just the last 3 bytes of IP address. Yeah, but anytime you do, so what you're saying is concatenate the two. Yeah, you could do that. You could concatenate MAC and IP to get a new address. But it's still one address, right? Yeah. Like for the postal system, people say, in the past, people have said, oh, in a house, there's multiple people. So even though it's the same address, then you make the person part of the address. Right? When I want to send you an address, I say, Benita so-and-so, this address, right? I don't just send it to the address with no name. Yeah, so that's actually part of the address. So you're saying concatenate, you can do that. Yeah, but right now, what we have is 2 different addressing mechanisms, and we're hacking them to be a little bit more efficient. Okay? Yeah, thank you for the question. Another question people have asked that no one asked here is, why not just expose the IP address to layer 2? Right? Yeah, it's possible. Yeah. There's no reason why you can't, right? This decision to do things at different layers is completely arbitrary. Yeah, so you could do that. Okay, good. Okay, let's just come back in a few minutes, okay? I just want to let everybody calm down a bit. You're all very excited, so just calm down a bit. Okay, let's get started. So, can I just get? Was that discussion? Was it fun? Was it interesting? Did you learn something? Yeah. Okay, good. So let's move on to transport layer. So remember the main job of transport layer is end-to-end reliability. So when we are talking about the functions at transport layer, try to connect them to end-to-end reliability. Okay, it'll help you understand it better. All right. Okay, so just a few things. So transport layer, there's a whole bunch of things that are related to end-to-end reliability. Things like detecting errors, reliable delivery, flow control, and congestion control. The 2 protocols that are used on the internet in terms of transport layer are TCP, Transmission Control Protocol, and UDP, User Datagram Protocol. If you go to other networks like Internet of Things or Bluetooth, and so on, right? You may not see things like TCP and UDP, but you will see the equivalent of a transport layer. Okay, so keep that in mind. So we also want to study the general, or understand the general mechanisms of transport layer. Okay, so transport layer sits in between application layer and network layer. And transport layer is a logical connection between two processes. So what we mean is there's a process that generates a packet, there's a protocol stack at the transmitter, and a protocol stack at the receiver. And we often think it's a logical connection between a process here. It allows the process here to talk to some other process at the receiver. Okay? Yeah, so I dwell too much on this. Yeah, so as I mentioned, there's going to be two main protocols, TCP and UDP. TCP is the protocol that implements all of the fancy mechanisms for reliability. UDP is a transport layer placeholder when you don't want reliability. But since there's a protocol stack, right? So there's a 7-layer stack or the TCP/IP stack for things to function nicely together, for devices to function together. Manufacturers have to follow a protocol stack, like a set of common rules. So even if you don't want the reliability, you need to have a transport layer in there. And UDP is what you put in when you don't want all the fancy reliability stuff. Okay? Okay, so what we're going to do is talk about a mechanism called multiplexing and demultiplexing. Now, this is a function that's not really connected to end-to-end reliability. But it has to be implemented somewhere. And, the powers that be, in their infinite wisdom, chose to put it at the transport layer. So this is the only mechanism that is not related to end-to-end reliability. Everything else we talk about. So we'll just talk about it, understand it, and shut the door on it, and never mention it again. Okay? It's called multiplexing and demultiplexing. And the idea is, so what I said last time, let's say this is my computer, and I have a network interface here. Okay? Well, all of the packets, and let's say there's a bunch of processes. All these are processes generating packets. All those packets go out this interface, right? Well, what is that called? You must have studied that in like some of your circuits classes or your digital design class. I'm taking all of these and putting them onto one wire. Yeah, what's that called? Multiplexing, right? So that's what's done, right? All of these packets are put onto this one wire. And then they come back. When they come back, what happens? They come back on this one wire or this one interface. What has to be done? What? Yeah, but so it's what I was telling someone before. Who was it? Winnie, right? Remember the mail packet comes back. Where does it have to go? To the mail tab, right? When the Instagram packet comes back, it has to go here. And YouTube, right? That's, as Olivier said correctly, that's demultiplexing. Now remember, your network interface has an address. The IP address. Okay, it has two, but it has a network address. Is that enough? Is a network address enough for me to get it back to the process? Like yes or no? Winnie, is the network address enough? No, right? So I need another addressing mechanism. So that's what is going to be shown here. So this other addressing mechanism is the idea of a port number. So it turns out there's actually three addresses, right? There's the IP MAC, and actually there's a port number that addresses a process. So the transport layer header is shown here. Okay, I'm showing you the transport layer header on the right. And we're going to do this for transport and for network. We're going to take the bits and chunk them into 32-bit chunks, 4 bytes, and we're going to stack them. And it turns out this is a useful way of doing it because many of the things are on 32-bit boundaries. Okay, so for visualization, it's useful. So both TCP and UDP, the first 32 bits are the 16-bit source port and the 16-bit destination port. That addresses the process. So when this node sends out a packet, and it's this process that sends out a packet, in the TCP header, the source port will be its port number. The destination port will be the destination port of the next hop. All right? Now, routing gives me the IP address of the next hop. So let's say this guy is a router that's connected to this LAN and to another LAN. It's like a bridge. So routing will tell this node the IP address of the next hop. Okay? But we know that for efficiency reasons, in a local area network, what do? We use the MAC address. So can anyone tell me, how does this node learn the MAC address of the next hop? It needs to do that, right? Routing only gives it the IP address of the next hop. There's a protocol for that. You maybe have heard it? Yeah, it's called ARP, Address Resolution Protocol. Okay, so the job of ARP is to tell this node from the IP address, which is gotten from the routing protocol at the network layer, what is the MAC address of the next hop. And that's because we want to use MAC address on an Ethernet. Okay, so then, so I get the port number, and that's what I populate in the destination port. And then you have the rest of the fields, whether it's TCP or UDP. When we talk about it, we'll talk about what's in the rest of the fields. Okay, but this is the idea of multiplexing and demultiplexing. And because we need to address a specific process, we need an additional addressing mechanism, which we call the port number. Okay, everybody good? And I think I mentioned to you before, many port numbers are reserved by the operating system. So all the low ports, the small port numbers, are all reserved. You're not allowed to use them. But the higher port numbers can be used. Okay, good? So for example, I think, does anyone know what port 22 is? Like, if you have used some network apps, you might have come across it. What's port 22? Wait, do you know? It's SSH. Okay, and yeah, I mentioned to you SMTP was 25, port 80. I think TCP is something. I don't know what. FTP is a certain port. I forget now. But all these applications, the let's say network type applications that are standard are assigned these low port numbers. Okay, any questions about this? Because if we're done, I think that's all I want to say. So that's it. I want to close the door on this. Everybody good? Okay, so this idea will come back again at the network layer because there's something called NAT, Network Address Translation. And it turns out NAT is going to hack port numbers. Okay, so one last thing, UDP. Again, I think we can do it very quickly, discuss it and put it to bed. UDP is a placeholder for transport layer protocol that has no reliability. Okay, it has, so this is the anatomy of the header of a TCP packet, of a UDP packet. You have source port, destination port. It turns out you still have a checksum, and then you have a length, and that's it. Nothing else. Everything else is just your data, your payload. We'll see TCP has a lot more. Okay, so that's pretty much it. So UDP, you could argue it has a little bit of reliability because of the checksum, but beyond that, nothing. There's no retransmissions, there's no acknowledgements. Whereas TCP will have retransmissions and acknowledgements. Okay, so you could ask the question, why would anyone use UDP? Well, you would use UDP when you want to have fine control over timing. TCP will turn out, it waits for a TCP packet to be built, and there's a little bit of delay. UDP, when you have real-time applications, it gives you get data, you just push it out. Now, these days, Skype, Facebook, WhatsApp, FaceTime, all use TCP, and yet they work pretty well, right? I think Zoom uses a combination of TCP and UDP. Okay, what else uses TCP? DNS. What else uses UDP? DNS. Domain name service is a way of mapping IP addresses, friendly names to IP addresses. Okay, so I think that's it. So we'll come back to UDP later when we want to look at the performance of transport layer, because you might have a mix of UDP and TCP flows, and it turns out that there's a difference because UDP flows are not nice. They just pump data in. TCP is going to do congestion control. So you can see there's going to be some interaction between UDP and TCP. So until that, we don't need to talk about UDP. We'll just talk about TCP. So we'll pick this up when we come back on Wednesday. Okay, we'll continue talking about TCP and all of the nice mechanisms that it has for end-to-end reliability. Okay, so that's the aim sort of for the next week and a half or so. Okay, thanks. I'll see you all on Wednesday. Sorry? Any tips? Homework one is quite straightforward, right? Is there anything in there? In fact, one of the questions is, why do we have MAC and IP addresses? The other ones, so for the homework, there's really no right or wrong answer. I just want you to think, right? It's a slightly open-ended, and you don't have to give me like novels. Don't give me little novellas. Like, be brief and concise. Spend your time thinking. Yeah, that would be my tip. Yeah. No, you submit it through assignments. There should be, I think I created all 3 assignments. Yeah. If you have any questions, you can ask. I will answer all questions, but what I'm not going to go spend time in class going through. You ask me questions. Can you just come? You mind just coming here? Let me turn this off.